And next part is called short GE. The guard intervals are required by OFDM between data blocks to protect data reliability and prevent a collision. The GE in 802.11a and .11g, which is 800 ns, while in 802.11n it has been reduced to 400, which improves the transmission rate because the space we used for the interval is smaller, right? So we can improve the rate. You can just think that in a road, for example, in a high-speed road, we have a lot of cars, and the distance between each car used to be, for example, it used to be 100 meters. So the speed is high, right? Is high. It's a high-speed street. But at this time, if we reduce the distance between two cars, for example, between each car, the distance has been reduced, which is 50. So the interval will occupy shorter distance or will occupy fewer rooms. And in this way, we can improve the speed, right, of this road. But do not think that the key is not the shorter, the better. For example, now the distance between two cars is 50, so we can improve the speed. And if we reduce it to 10 meters, of course we can improve the speed, but at the same time, it's becoming very dangerous, right? And even we reduce it to 1 meter, so it's very possible for them to crash, right? So the key is not the shorter the better. Okay, and for a spatial stream, the throughput is improved by 10% from 65 Mbps to 72.2 Mbps since the GE has been reduced. And short GE is suitable for scenarios with good RF conditions. In scenarios with a strong multipass effect, it is not recommended because the shorter GE will make it more serious when the multipass effect is strong. Okay, and next is about the 14 MHz bandwidth. 802.11n defines the standards of both the 2.4 and the 5 GHz bands. In 802.11a, B, G, each channel occupies 20 MHz bandwidth. As we can see at the first line, the bandwidth of each channel, actually this is you can think this is channel 1, channel 2, channel 3, channel 4, and each of them, the bandwidth is 20 MHz. While in 802.11n, there are two bandwidths, except 20 MHz, another is 14 MHz wide channel. You can see each channel here is 40 MHz, and this is 40 MHz. Since the bandwidth has improved, so the rate will be improved at the same time, right? And next, let's see the channel binding. The 40 MHz bandwidth can be achieved by binding two 20 MHz bandwidth channels, right? Because as what we can see in this figure, if the bandwidth is 20, so we have 4 channels, and if we want 40 MHz bandwidth, so we can bind two 20 MHz bandwidth channels into one, so we can improve the bandwidth. And increasing the throughput by more than 2 times that of the 20 MHz bandwidth. Pay attention here. The bandwidth has improved 2 times, right? But why the throughput is more than 2 times. You can think about it. Why? Why is more than 2 times? From the figure in the former page, we can figure it out. You can see when the bandwidth is 20 megahertz, you can see here between these channels, actually there are some intervals. But if we bind channel 1 and channel 2 into one channel, you can see this interval is still exists. This is exists, but the interval here has disappeared. So we have actually improved the usage of this channel. This is the reason why we see that the throughput is more than 2 times than that of the 20 megahertz bandwidth. Okay, this is called channel binding. And the most important here is you should know why it's more than 2 times. Okay, next is about the 20 megahertz bandwidth rate and the 40 megahertz bandwidth rate. For the 20 megahertz bandwidth, if it's a single stream, the speed is 65 Mbps, and the dual stream, the speed or the rate is 130. 3 streams is 3 times of the single stream, so 3 times 65 would be 195. 4 streams would be 260. For the 40 megahertz bandwidth is similar. The single stream rate would be 150, so the downstream would be 300. 3 streams would be 450, and 4 streams would be 600 megabps. Okay, this is about the bandwidth rate for different bandwidths and the different number of streams. And next is called MIMO. MIMO, short for multi-input, multi-output. From the name, we can know that MIMO is a kind of technology that supports different numbers of input streams and different numbers of output streams. It's a technology that transmitter and receiver use multiple antennas to transmit and receive data, improving communications quality and the volume of data that can be transmitted. By using the spatial diversity technique, the receiver can receive signals from multiple antennas, ensuring signal reliability and performance. Using the spatial multiplexing technique, the transmitter converts the serial data to be transmitted to parallel data and transmits the data from multi-antennas. MIMO improves the volume of the data that can be transmitted without using additional spectra. When transmitting data, MIMO allocates multiple spatial streams to separate antennas. The most distinctive feature of MIMO is the usage of multiple antennas. Because, for example, this AP, you can see it has 6 antennas, right? So we can use multiple antennas to communicate with another device. By using MIMO, it supports up to 4 spatial streams, right? And 4 times 4 means 4 streams is used to transmit. Another 4 is used to receive. The more spatial streams, the higher power consumption. So if we use a MIMO technology, we should take the power consumption into consideration. And if we use 802.11n, it supports the MIMO energy saving mode. Use multipass only when there is a high demand for performance, because the power consumption is high, right? Okay, this is an overview of MIMO technology. And then let's see the transmitting and receiving spatial streams using MIMO. Now on the left is a transmitter, and on the right is a receiver. Each of them have many antennas. So they support multiple spatial streams to communicate. And 1 times 1 means one antenna transmits, one receives. And they will build one spatial stream. Except the 1 times 1, here you can find 1 times 2, 2 times 2, 2 times 3, 3 times 3, 4 times 4. So the number represents how many antennas are used to receive and how many are used to forward. Okay, and different number of antennas will build different number of streams. By using MIMO technology, we can establish multiple streams between the transmitter and the receiver. So at this page, it shows us if we have one antenna for transmission, another one antenna for receiving, so we could establish one spatial stream. While if 1 times 2 means one antenna for transmit, another 2 for receive, so we could establish one spatial stream. And at this time, the system dynamically selects the optimal transmission unit out of the 2 transmission units. And if 2 antenna transmit, 2 antenna receive, so we could establish 2 spatial streams, and 2 times 3, 3 times 3, 4 times 4, and so on. Okay, this is about the transmission streams. And then, if we use MIMO technology, it has multiple advantages. It improves channel capacity. What's more, it is conducive to channel reliability and bit error rate reduction. The former is based on the spatial multiplexing of MIMO channels, and the latter is based on the spatial diversity of MIMO channels. Okay, so by using MIMO technology, we can not just improve the reliability of the channel, and we can also reduce bit error rates. Okay, this is about the MIMO advantages. And in the 802.11 standard, it uses OFDM and MIMO at the same time. And let's see how that works. The MIMO technology increases network bandwidth. It divides an IP data packet into multiple short pieces of data and uses multiple antennas to transmit the pieces simultaneously. The receiver receives the data pieces using multiple antennas and recombines the data. The rate could be up to 824 Mbps. So it's a very high speed, right? From this figure, we can see the original data has been divided into data piece 1 and the data piece 2. Between the transmitter and the receiver, there could be 2 spatial streams. Spatial stream 1 is green, spatial stream 2 is yellow, and it will transmit signals to the receiver. And of course, after receiving that, the receiver will restore the data, right? So we can get the restored data. And in this way, we have improved the network bandwidth, and the data transmission rate has been improved a lot, even up to 624 Mbps. Okay, this is application of it in 802.11n. Okay, and then let's see, subcarrier OFDM modulation. This technology is used in 802.11a, .11g, and .11n. In 802.11a and g, a total of 52 subcarriers are available. While among these 52 subcarriers, 48 of them are data subcarriers, means 48 subcarriers are used to send the data, while 4 as payload subcarriers are used to transmit some control plane messages. While in 802.11n standards, a total of 56 subcarriers are available. And among these 56 subcarriers, 52 of them are data subcarriers and 4 are payload subcarriers. So the rate, you can see the rate has been improved to 58.5 megabps. How can you calculate is that each channel offers the same rate, while here we have 4 more channels, 4 more subcarriers. So the rate has been improved, right? And the number is 58.5 megabps. Okay, this is about the subcarrier OFDM modulation. And then let's see the MCS. MCS is a modulation and coding scheme. You can see here, based on different spatial streams, different types of modulation, bit rate, and the bandwidth, even the number of key is different. So the rate we can find here is different. For example, let's say that MCS 0, which have 1 spatial streams, the modulation mode is BPSK, the bit rate is half, and if the bandwidth 20 MHz, G is 800 ns, so the rate would be 60.5 megabps. While if the modulation is QPSK, so the speed is 13. So we can find in this table, actually it's a relationship of the rate and multiple parameters here. And in 802.11n, the physical rate depends on modulation, the code rate, number of spatial streams, support for 40 MHz bandwidth, and more than 300 rates are available considering all these factors. When there are 4 spatial streams, the physical rate could reach even 600 megabps. You can see here, 600. And 802.11 has only 8 basic rates, 6.5, 13, 19.5, 26, 39, 52, 58.5, and 65, which can be found here. Okay, this is the basic rate of 802.11n. And based on these rates, we can modify some of the parameters. For example, we can modify the modulation, we can modify the bit rate so that we can improve the speed, even up to 600 Mbps. Okay, this is about MCS. Okay, the next is maximal ratio combining. We call it MRC. When receiving signals using multiple antennas, the receiver weighs and aggregates the signal. In this figure, you can see here, this receiver have 3 antennas, right? And each antenna will receive a signal. So after receiving these signals, the signal from the optimal path is weighted the most. For example, the weight of this signal is, we assume that the signal is 8, and this is 2, maybe this is 3. So this number of weights will be used to calculate. And from the number here, you can find, of course, the signal with highest weight will affect the results. And from here, you can find the signal with the highest weight will bring huge effect to the results. So that since the number of rate is related to the signal quality, so in this way, MRC allows the receiver to get a preferable signal out of multiple unsatisfactory signals. And after MRC, the quality of the signal, you can see here, has improved a lot, right? Even from the figure, we can figure it out. Okay, this is about MRC. And next, let's see the Ethernet CSMA CD. In the Ethernet, to prevent collisions, we have a solution which is called CSMA CD. It means that each time when a transmitter wants to transmit data, it will firstly monitor or detect the channel to find is there someone else using it at this time. If the channel is idle, it will wait for 9.6 microseconds, and then it will send the frame. While if the channel is not idle, because someone is using it, so it will keep monitoring or keep detection. Okay, and after sending the frame, it will monitor the channel 2, because we should find out is there collisions occurred or not. If no collisions, so we should confirm if data has been transmitted. Yes, so we have finished the data transmission. If it's no, so we will continue, right, until we finish the data transmit. But while if we have caused collisions after sending out frames, so we will send out a 32-bit congestion signal. And at the same time, we will record the time, how many times we have caused collisions, right? And while if the number is greater than 15, means the congestion is heavy, and we will end the transmission until the channel is not that busy or until the channel is idle. Okay, while if the number of K is smaller than 15, so we will wait for a random time and then transmit the data again. This is a working process of CSMA CD in the Ethernet. Okay, the reason why we introduce it here, because we want to introduce the CSMA CA principles, which is used in the wireless network. Okay, let's see the process. Before transmitting data, the STA monitors the medium status and transmit data after a DIFS and a random duration during which the channel remains idle. So you can see, before we send out frames, firstly we should detect, is the channel idle or not? If the channel is idle, so we should wait for DIFS, wait for interval. And then, before we send out the frame or send out the data, we should send the RTS firstly. RTS means request, right? It's a request to send packets. And after sending out the RTS, we will reset the timer. The timer is used to record the time that how long I have sent the RTS. For example, I have sent the RTS for maybe 1 second or 2 seconds. And for example, this is the time that how long we have sent the RTS. And then after sending out the RTS, we should receive CTS before we forward the data, because CTS is kind of acknowledgement or a kind of confirmation. Okay, so after we set the timer, we will see if we have received the CTS before the timeout. No, if the result is no, means we did not receive the permission before the time's out, means we are not allowed to transmit data. But if the result is yes, means we have got the permission to send the data. So we will wait for SIFS, wait for another interval, and then send the frames. After sending the frame, we will reset the timer again. And because I don't know if you still remember that we said in the wireless network, Each time when we receive a frame, we should respond with acknowledgement with ACK. So the function of this timer is that we should monitor if we have received an ACK before timeout. If we received it, means the receiver has received the frame, so end. But if no, so we will record the time. How many times we have filled to forward the frame. If the number, for example, if the number is greater than 15, so means we will finish the data forwarding because it's too busy. Okay, while if the number is not greater than 15, so we will calculate the backoff and wait for some time, then repeat the whole process. So this is a CSMA CA working principle. It's a little more complex than CSMA CD, right? But I think it's easy for you to understand this process. And from this working principle, you can also find that actually CSMA CA, in fact, is a channel appointment mechanism. Because if we want to send a frame, so we should firstly find out if the channel is idle. If it's idle, so then we will appoint for this channel because we will send an RTS to request. So it means that if I can use this channel or not, once I receive the CTS means, yes, you can use this channel. So it's a kind of channel appointment mechanism before data transmission. And in this way, we can avoid collisions in the wireless network. Okay, this is about the CSMA CA mechanism. And the next concept is called IFS. After transmitting data, all stations must wait for a short time before transmitting new frames. The short time is called interframe space. We call it IFS. And the IFS is independent on the type of frame transmitted. The IFS is short for high priority frames. Means that if the frame has a higher priority, so it would wait for a short time. We assume that this is a bridge, right? This is a bridge. And now we have a lot of cars. For example, we have a lot of cars. This is car 1, car 2, car 3. And each car wanna cross this bridge. Okay, so for example, this is a car, he has crossed this bridge. So now at this time, the bridge is idle. And all the cars should wait for a short time. For example, after this car 0 cross the bridge, car 1, car 2, car 3 wanna cross it. But each of them should wait for a short time. And car 1 just need to wait for 1 second. Car 2 needs to wait for 10 seconds. And car 3 needs to wait for 15 seconds. So in this scenario, which car will be the next one that crosses bridge? Obviously, it will be car 1, right? So for the frames, it's the same. If the frame has a higher priority, so it needs to wait is shorter. It will be transmitted. Okay. So this is what we mean here. If high priority frames reach the medium before low priority frames are deferred to reduce the possibility of a collision. Okay, so this is about IFS, and you should know higher priority indicates shorter IFS. Okay, this is about the WLAN basics, and about this part, here is a question. MAC is a sublayer of the TCP/IP network layer. About this statement, you think it's true or false? And if you think it's false, Can you modify it? Okay, of course, it's false, right? It's very obvious. The reason why is that MAC is a sublayer of the TCP/IP data link layer, not network layer, right? Data link. Okay, this is about the WLAN basics, and that's all for this part.